So we got cut off just a little bit at the end there, but I wanted to show you how to do chi-square values for both of them. And it's a little bit messy, I gotta be honest. That's just the way the chi-square is. But let me reiterate that I used chi-square inverse with that alpha degrees of freedom. Then I used chi-squared dot inverse dot RT for the other one, again with that same alpha and degrees of freedom. That's the beautiful thing about the new way. The new Excel 2010 just finds both numbers, and it finds them using those two separate functions. Now the old Excel 2007 and earlier, just had this one function, chi inverse, CHIINV. So you had to find each one of them separately for alpha and 1 minus alpha over 2. And that's what you type. So you say chi inverse 1 minus alpha over 2 B6, and there you go. So it's a little bit odd, but you've got both of them right there. So there you go. Okay. Technically, this one is the 1 minus alpha over 2. Let me just put that in there. Is equal to the 7.26. And then chi alpha over 2 is equal to 24.99. 996, I think it was. Okay? So those two values are your critical values. And notice they're both greater than 0, and they're not even remotely symmetric. It's not like one of them is 7.26 and the other one's negative 7.26, something like that. All right, so this is the formula now for the confidence interval. Now that we know how to find these critical values with Excel, we can find these confidence intervals for the variance, and then this is the one for the standard deviation. Notice they're the same thing, it's just that the standard deviation ones have square roots. Simple as that. Okay, so I have these scores in here for the GRE. These are the scores for the verbal portion. The verbal reasoning portion of the GRE is normally distributed with a mean of 469 and a standard deviation of 120. Suppose a random sample of 10 students took the test and their scores are given below. There they are. So first thing, verify that this data is normally distributed by constructing a normal probability plot. Why is this necessary? Okay, first of all, if you look up at this, the blue box, it says that the simple random sample size n is taken from a normal population. See? So you have to know that the data is normal. So first of all, the data is normal, which is needed in order to be able to make confidence intervals for either the variance or standard deviation. Got it? All right, then determine the point estimate for the population variance and for the population standard deviation. Okay, so the point estimate for the variance would be, well, let's go find it, shall we? Now I've got the data in here. I just kind of typed it in right here. So let's do the variance, and let's do standard deviation. Variance, of course, we know how to find its variance. It's a sample, so var.s, or old school Excel, it's just variance, VAR, that's it. There we go. And then standard deviation would be equal STDEV. For me, because I'm in the new Excel, it's just STDEV.s, but if you're in the old, it'll be just STDEV. Remember how we found that way back in chapter 3 for that data? And there we go. So our variance and our standard deviation, those are our point estimates. They're our single best guesses for what sigma and sigma squared will be. Actually, sigma squared and sigma respectively. Now, construct that confidence interval for the population variance. So I'm going to grab this and type that in here. Hold on, let me go type it and I'll be right back. There's the formula. Now realize what this means. This is equal to n minus 1, which for us is how much? Let's think. How big was our sample? It was 1, 2, 3, 10 students. So n minus 1 would be 9 for both of them. And s squared, we just found it was 110. Oh, Lord, all that. So I'll just put that in there. Oops, and we'll have to finish this up next time. We're out of time.